Today we'll be looking at plasma, the mysterious and powerful fourth phase of matter. If you're new to this channel, welcome. This is Mr. Singularity, where we explore the scientific and technological breakthroughs shaping the future as we know it. My instructor taught me when I was in primary school that matter occurs in three potential states: solid, liquid and air. She neglected to mention plasma, a particular type of electrified gas that is itself a state. We rarely encounter natural plasma unless we are lucky enough to see the northern lights, or if we look at the sun through a special filter, or poke our heads out of the window during a storm of lightning, as I liked to do when I was a child. But hydrogen, with all its obscurity in our everyday lives, makes up more than 99% of the universe's visible matter, i.e. if we disregard dark matter. Plasma physics is a rich and diverse field of inquiry with a special twist of its own. In some areas of science, intellectual vitality comes from the beauty of grand theories and the search for deep underlying laws, as evidenced by the account of gravity and general relativity by Albert Einstein, or the attempt by string theorists to replace the standard model of subatomic particles with tiny oscillating energy strands. The study of plasmas also enjoys some remarkably elegant mathematical constructions, but, unlike its scientific cousins, its applications to the real world are mostly driven by that. But first, how do you manufacture a plasma? Imagine heating up an ice-filled tub and watching it move from concrete to liquid to fire. As the temperature rises, the molecules of water become more energetic and excitable and move more and more freely around. When you keep going, the atoms themselves will begin to fall down at anything like 12,000 degrees Celsius. Electrons are stripped from their nuclei, leaving behind charged particles known as ions that swirl about an electron's resulting soup. It is the condition of the plasma. Blood connection to physical plasma is more than mere coincidence. The American chemist Irving Langmuir observed in 1927 that the manner in which plasmas carried electrons, ions, molecules, and other impurities was similar to how blood plasma ferries around red and white blood cells and germs. Langmuir was a pioneer in plasma study. He also discovered with his colleague Louis Tonks that plasmas are characterized by swift oscillations of their electrons due to the collective behavior of the particles. Another interesting property of plasmas is their capacity to support so-called hydromagnetic waves, bulges that move along magnetic field lines through the plasma, similar to how vibrations travel along a string of guitars. The physics community was skeptical when Heinz Alfvén, the Swedish scientist and eventual Nobel Prize winner, first proposed the existence of these waves in 1942. Yet, after Alfvén had delivered a lecture at the University of Chicago, he was asked by the legendary scientist and faculty member Enrico Fermi to explore the idea, conceding that these waves may of course occur. Scientific consensus has been that from that moment on, Alfvén was absolutely correct. But this isn't even the most complicated bit. We managed to reach those temperatures in the 1990s and beyond. Worst of all, hot plasma is very unstable and doesn't like staying at a fixed volume, which means it's hard to contain and make useful. In the early 1950s, efforts to achieve guided thermonuclear fusion date back to then. At the time, both the US and the Soviet Union and Great Britain undertook research secretly. Princeton University in the US has been the centerpiece for this research. There, physicist Lyman Spitzer began Project Matterhorn, where a clandestine coterie of scientists attempted to ignite and concentrate fusion into a figure-8 shaped system dubbed a stellarator. They had no hardware, so they had to focus solely on pen and paper calculations. Even though they didn't solve the puzzle, they ended up developing the energy principle, which remains a powerful method of testing a plasma's ideal stability. In the meantime, scientists in the Soviet Union were developing a different device, the tokamak. Designed by physicists Andrei Sakharov and Igor Tamm, this machine employed a strong magnetic field to corral hot plasma into a donut shape. The tokamak was better at keeping the plasma hot and stable, and most fusion research programs still rely on the tokamak design to this day. To that end, a consortium of China, the EU, India, Japan, Korea, Russia and the US have joined forces to build the world's largest tokamak reactor, which is expected to open in 2025. Yet, there has also been a growing interest for stellarators in recent years, and the biggest opened in the world in Germany in 2015. Investing in all fusion routes would certainly give us our best shot of potentially achieving progress. Plasma is often intertwined with space physics across Earth, where the stuff is carried across the vacuum on the winds produced in the Sun's upper atmosphere. We're fortunate that the Earth's magnetic field is protecting us from activated plasma particles and harmful solar wind rays, but all of our rockets, spacecraft and astronauts remain vulnerable. Throughout this violent climate, their capacity to live depends on knowing and adapting ourselves to the nuances of plasma. In a new field known as space weather, plasma physics plays a similar role in terrestrial atmospheric conditions to that of fluid dynamics. Most of my work has been dedicated to something called magnetic reconnection, where the magnetic field lines in the plasma will break and reconnect, contributing to a sudden release of electricity. This cycle is assumed to cause eruptive events in the atmospheres, such as solar flares, although thorough knowledge remains elusive. We may be able to forecast solar storms in a way similar to how we foresee poor weather in towns, possibly in the future. Looking back and not forward, in space and time, my hope is that plasma physics will provide insight into how stars, galaxies, and clusters of galaxies first formed. Plasma was pervasive in the early universe according to the standard cosmological model. Then everything started to cool and charged electrons and protons together to make electrically neutral atoms of hydrogen. This state persisted until the first stars and black holes were created and radiation started to release, after which the cosmos reionized and reverted to a largely plasma environment. Finally, plasmas help to explain some of the most spectacular phenomena we've seen in the cosmos' remotest regions. Consider the faraway black holes, huge structures so large that they cannot withstand even light. To direct observation, they are practically invisible. Yet black holes are usually encircled by a spinning disk of liquid matter, moving inside the gravitational force of the black hole and releasing high-energy photons that can be detected in the X-ray range, showing more about this intense atmosphere. It's been a thrilling ride for me since the days when I felt solids, liquids and gases were the only question of form. Plasmas still seem rather exotic, but as we learn to exploit their potential and broaden our view of the cosmos, they might one day appear to us as normal as ice and water, and if we ever achieve controlled nuclear fusion, plasmas could be something without which we can no longer live. If you have made it this far in the video, thank you and welcome to the end of the video club. What's your take on this? Let me know down in the comments below and check out one of these other videos. This has been Mr. Singularity, and I'll see you on the next one.